Yes, I think we are live. Can you cross check once? Obigyan or something?
Yes, sir, we are live.
Yeah, Obigyan, you can start.
Okay, sir. So, hello, welcome, and good evening to everyone. This is the 24th AI Technical Lecture Series, and today we have Dr. Ayon Borthakur, sir, who will be giving us a talk titled "How Can Neuroscience Aid in Designing a Model Computer?" So, Dr. Ayan Borthakur is currently working as an assistant professor in the Department of Artificial Intelligence at IIT Hyderabad. Previously, he worked at Inatera Nanosystems in the Netherlands as a senior neuromorphic engineer in machine learning. At Inatera, he worked on marrying deep learning and analog computing towards ultra low power and latency radar target recognition, which resulted in multiple patent applications. Before that, he completed his PhD at Cornell University. As part of his PhD, he worked on neuroscience-inspired artificial intelligence for learning in the wild, focusing on its implementation in neuromorphic chips such as Intel Loihi. His PhD work is part of an international patent sponsored by Cornell. He completed his Bachelor's of Technology in Electrical Engineering from IIT Dhanbad. So, without any further ado, I'd like to hand over to talk to Dr. N. Bhattacharya, sir.
Okay, so
Ayan,
please.
sir, 1 second. Can you reshare your screen once?
Okay, you are having issues there?
Yeah, you stop.
Okay, let me try it again. So, is it working now?
Just one second.
Oh, take it. Sorry for some technical delay. Ayan, just 1 second. Can you reshare once?
See data target recognition, which results.
Ayon, can you reshare once? Yeah, Ayon, you can go ahead. Sorry for the delay. Yeah, thank you.
It's good now, right?
Yeah, we can go ahead.
Okay, so it's 7:10. So I'll have to give something short. So hello everyone. So before I start, I have a quick question for you guys. So I see like there are like 5 people here and there are some on YouTube. So are you guys familiar with neuroscience? Like something about neuroscience and neurographic computing? Or is it like nothing? What should I assume?
Yeah, maybe little bit.
Okay, that's fine. I just want to have a sense of. Okay, so guys, today I'm going to talk about how can neuroscience help design a model computer. This is very new probably to guys. That is fine. By the end of my talk, you'll understand a lot of those things. So don't worry. Just follow my talk. So I'm skipping this intro because you gave it. So what is this research about? So this is about overcoming software and hardware limitations of AI by taking inspiration from the brain. So you have this rodent. He has a brain. We take inspiration from the rodent and we design AI algorithms. As part of it, we design hardwares, we design softwares, both. That's the research. Now we are talking about AI. So you can design AI in multiple ways. Imagine you have this axis here. So you have this axis going from 0 to 1, say. On the extreme limit, you can assume that you're not looking at neuroscience at all. You say, I'm not going to care about neuroscience. I'll design algorithms, AI algorithms without neuroscience. That is also fine. People do that. Algorithms like XGBoost are like that, or say random forest. They are not neuro-inspired, mostly. Then there is other extreme direction where you find appropriate substrates to build an artificial brain. You can probably try to build a rodent too. People are working on this. And that is also a good direction, maybe. Or you can be somewhere in between. We are somewhere in between because we mostly try to design AI systems for silicon. I would say we are here somewhere along this axis. It's with this like 0.8, we are 0.8, something like that. So today most of the talk will be positioning here. So we'll know neuroscience, we'll know machine learning, but we'll try to design neuro-inspired AI by standing here along this axis. Why? Because you want to understand the architectural priors and the learning mechanisms supporting learning in the wild. I put an asterisk here because you're going to understand this by the end of my talk. And then there we have a second goal. We want to implement in various embedded AI chips. So embedded AI chips, again, I'm going to explain after some time. Keep in mind, AI inspired by neuroscience is not at all equal to computational neuroscience. There are similarities, but there are also a lot of differences. Now, we have been talking about this immortal computing. Let's start with understanding what is immortal computing. So these are not my words. I'm going to tell whose words are there. So immortal computing, the software should be separable from the hardware so that the same program or the same set of weights can be run on a different physical copy of the hardware. In short, you can say the knowledge does not die when the hardware dies. So you have a software copy which you can implement in millions of chips. And this is what most of the AI is right now. This is fine. So you are designing an algorithm and you are designing inference applications. You are putting the same algorithm on multiple chips, millions of chips. and we are selling it. This is a very profitable research direction these days. That's fine. This is immortal computing. What is a mortal computer? Is something, the concept is old, but this word has been coined recently, I believe. This is from this paper from Jeffrey Hinton in Europe this year, the forward algorithm. So in Jeffrey Hinton's words, he says, if, however, we are willing to abandon immortality, it should be possible to achieve high savings, huge savings in the energy required to perform a computation, and the cost of fabricating the hardware that executes the computation. Now, there are a lot of words here, so don't worry, later there won't be so many words. I'm just describing this mortal computing here first. We can allow large and unknown variations in the connectivity and nonlinearities of different instances of hardware that are intended to perform the same task and rely on a learning procedure to discover parameter values that make effective use of the unknown properties of each particular instance of the hardware. Don't worry about this. We'll understand this after some time. Basically, we are trying to design an AI algorithm only for a particular chip. So we put a network, which is partially trained, something like that, and then you put it on a hardware. It's going to be better with time. This is the same way the brain works. We don't learn everything when you're born. We learn over lifetime. And the way we respond to some stimulus is different from the way my friend responds. Now, these parameter values are only useful for that specific hardware instance. So the computation they perform is mortal. As soon as the hardware dies, the computation is gone. That particular learning is gone. So this is mortal computing. Why and where we are envisioning this will be useful? This will be useful for putting something like GPT-3 in your toaster for $1. If you want to reduce the cost, if you want to reduce the power consumption, if you want to do it at a high speed, then you will need this kind of algorithms. Now, this mortal computers is actually indirectly referring to neuromorphic engineering or computing, which has been going on. This kind of research is going on since like late 1980s. So they are similar terms. So they're similar things. So I'm going to talk about neuromorphic engineering now. So we hear a lot about neuromorphic engineering. What exactly is this? So the person you see here is Government. He's a professor at Caltech, now emeritus. He pioneered VLSI design. Because of this invention, we can now pack huge number of transistors into a single silicon chip. He also developed neuromorphic engineering in late 1980s. He was a visionary. He said that, okay, we designed this, but we also need to think about what will be the roadblocks in like 10, 20 years from now. So we need to think something different. So he started thinking about neuromorphic engineering. His motivation was reduce chip power consumption by mimicking the massively parallel computing architecture of the brain. Keep in mind, this was in the late 1980s, and we didn't know much about the brain at that time. We know much more now, going to some new tools like optogenetics. So what is neuromorphic engineering? You have this brain here, and then we have these beautiful pictures of the neurons and synapses from a person called Ramon Cajal. And then we have on the right here 2 recent neuromorphic chips. One of them is Intel Loihi, the smaller version is Kapahobei, and the IBM Turnoff. Neuromorphic engineering is concerned with creating computing devices mimicking the biological nervous system. Why? To build efficient neural network processing systems. And then there is a secondary goal to understand the brain by implementing it in silicon. So you want to understand the brain by designing it. Both of them are violent directions. I am primarily concerned with building efficient neural network processing systems. That is mostly my research. I also have a paper on the other directions, but that's a separate thing. Now, why neuromorphic? Like we already have so many startups, companies working on hardware. So we have TPUs. Why do we care about neuromorphic? So on the left, you see this IBM supercomputer, 13 billion watt power consumption, 5,600 square feet, and 340 tons. Same computation can be performed by brain, consuming 20 watts, 2 square feet, and 1.4 kg. The numbers are a bit debatable, but the idea is there that brain can done the same computations in a much efficient way. It cannot do everything. That is why we care about neuromorphic. Now we are focused right now on resource constant AI. That is one of my main research area. Say we want to put AI in mobile personal assistants or in embedded devices, say in drones, or medical and health wearables, and real prosthetics. There you will be doing AI. You care about you'll be learning and inferring. There you need low power. That's why neuromorphic becomes important. And actually, designing these low power systems is an open issue. This is a very active area of research, but there are also many challenges here. And in this kind of scenarios, there's also possible privacy and latency issues when you're using cloud. So like in Europe, people don't like to share their data. So they don't like it when you put the data on cloud in like somewhere in the US. So if you want to do it without cloud, then this is the way to go. This is one direction. So neuromorphic presently is enabling a lot of such applications. But this is neuromorphic in the current way. Like we are learning and we are doing inference. There are a lot of things for the future, which I'm going to talk about. So currently, what are the neuromorphic chips? This is again a very brief intro. So you have IBM True North on the Intel Loihi in the middle, and then you have the brain chip one. These are all digital neuromorphic chips. Then there are two analog neuromorphic chips from Inatura and Sensense. Usually, digital analog neuromorphic chips are at least 100 times more power efficient than digital, but they have their own challenges. But when we say mortal computing, we actually are referring to analog neuromorphic. And some of the common features are they consume low power and they're low latency. And most of them have spiking neural network architectures. Doesn't have to be there. I didn't mention here, but there are some neuromorphic chips which are not doing spiking neural network. That is also possible. And the goal is to achieve general purpose neuromorphic systems, which you will understand after some time. So you cannot have a chip for only one application. Ideally, you should have tens of fifties of applications. That is how you can benefit from selling a chip. So what is this neuromorphic engineering? Let's go into the science part of it. What you see on the left is a biological neuron. It's something we learned in our 10th standard. So you have a dendrite receiving the information processed by the soma, goes along the axon, and it is sent to the other neuron. What you see on the right here is a silicon neuron. And it has been observed that the physics of silicon can be exploited for application of neural dynamics. What do I mean by that? So here the x-axis is time, and the y-axis is mammalian potential evolution. This kind of mammalian potential evolution dynamics are observed in biological neuron and can be observed in silicon neuron too. So neurons and synapses form the computing units of neuromorphic chips. They're suitable for massively parallel tasks. There are some other characteristics of neuromorphic engineering too. You have this analog neuron that I showed you before. What you see in the middle is a transistor. So transistors, if you don't know, are widely used to form circuits in CPUs and cell phones. And in cell phones or in CPUs, transistors are operated in above threshold domain. So the gate to source voltage here. So transistors have a gate here, which is VC here, and a source and a drain. Their voltage and their corresponding current are quite high in our conventional CPUs. But when you operate it in neuromorphic and analog neuromorphic chips, they're operated in sub-threshold domain, which means the current flow is low. So the power consumption is lower, which means if you have a lot of those transistors, the power consumption will be super low compared to conventional computing architectures. So the sub-threshold dynamics are exploited to mimic biology here in this neuromorphic chips using sub-threshold dynamics. And this is an interesting observation. The biological dynamics can be observed in analog neuromorphic chips in transistors when they're operated in sub-threshold domain. So this is one characteristic. There's one more characteristic of neuromorphic engineering. In our conventional computers, we have a CPU, you have a memory, separated by bus. This is a bottleneck. This is called von Neumann computing architectures. In neuromorphic computers, you have a neuron and you have a synapse, and they're co-localized. Computation is co-localized. You don't have this bottleneck. This enables massively parallel computations. It also ensures extremely low power and low latency computations. Now, this is cool. These are hardwares. The field started with designing hardwares, the field of neuromorphic engineering. This started in 1989 and early 2000s. But there's a dearth of commercially viable neuromorphic algorithms. And it's obvious. We knew about neurons and synapses. We designed these hardwares, but what is the use of it? That's where the knowledge of neuroscience comes. We need to understand the brain better. We need to make use of this information and find applications for these neuromorphic chips. Not only this, but there are other neuromorphic chips too. So why? Why is it hard? Why there is a shortage of algorithms? Neuromorphic algorithm is a radically different approach of designing algorithms, just enter neuromorphic. One reason is, in machine learning, we are kind of used to doing tensor multiplications. We are kind of addicted to it. We do tensor multiplication using PyTorch, TensorFlow. We don't even care. But in this neuromorphic chips, there is no multiply and accumulate operations. No tensor multiplications by default. Instead, the network update is happening based upon spikes. There is spike-based communication happening. That makes it difficult to think about algorithm design. So what are people doing? So since 2017-18, even before that, but most of the work has started since 2016 and 17. One of the research direction people take is, which is like a holy grail right now, but there's a lot of limitations. ANN to SNN conversion. ANN means artificial neural network, and then you convert it to a neuromorphic network, which we call it spiking neural network, in short, SNN. What they do is they train an artificial neural network with backprop. That's what we do right now. And then they adjust the weights and threshold values, and then they convert to SNN. Now, a lot of work is going on, but there are a lot of limitations here in this approach. Like the latency is very high. But this is an active research area. Other area which people do is surrogate gradient decision. I have been working a lot in this direction for the last 2 years, even at IIT Hyderabad. And I'm going to talk very briefly about this today. So we actually take a neuromorphic network, spiking neural network, and we train using backprop, using some approximations. And there's some tricks. And it has been observed that neuroscience can help us optimize this network. And this is, again, a very active research area. The limitation is because we are using backpropagation through time, it consumes a lot of memory. And there are some other limitations too. But the advantage is that it consumes really low power. Let me come back to that later. So my focus first today is biology-inspired networks. Again, this is a patent at Cornell University. And in order to develop this, you also need a software framework. So we developed Sapinet, which is a Python-based framework for neuromorphic modeling. It is available on PyPy. A month from now, I think we will be having the next version of Sapinet ready. And you guys should be able to use it. Now, this work was done at Cornell University. Now we have started working here. It gained a lot of media attention at that time. So we covered in the communications of the ACM and some other places. So let's get back. Okay, that's fine. So what is this research? So this is a complicated thing. As you can imagine, we need to understand neuroscience, we need to understand hardware, and need to understand machine learning and some other things too. So what we do, we have multiple people working on it. Some people try to understand neuroscience. Some people try to explore applications. Some people are working on designing neuromorphic AI algorithms. And then there are some people who are trying to evaluate those algorithms on practical settings. Once you complete an iteration cycle, you move to kind of product development. You have to design software. You also think about how to optimize the hardware. This is how neuromorphic AI is done, especially in my lab and like the people whom I'm working with. Now, this is again a very big topic. What we are focused right now? Right now, we are focusing on something very simple. In traditional embedded AI, sensor embedded AI systems, we have a sensor here. And then we have a processor, which goes to an actuator. We want to convert the sensor into a neuromorphic sensor, which I'll probably describe later. And then the processing, we want to do it in a neuromorphic processor. Unlike a conventional process in machine learning accelerator, we want to do it in neuromorphic processor like Intel Loihi or some analog chips to reduce the power consumption, to reduce the latency. And there are other benefits too, which I'll come to that later, which goes to an actuator and acts on it. But that's not the only thing, as I say. If you have to do it neuromorphic, we are talking about the brain. So we need a reference system, right? So we use the brain as a reference system to move fast, but that doesn't have to be. Here in neuromorphic computing, there are also physicists who have come up with really cool ideas. There are chemical engineers who have come up with cool ideas, and we usually are open to all those ideas. We need to an end-to-end understanding of the system. Only knowledge of neurons and synapses is not enough. We need to understand the system as a whole. We need to connect the understanding to the microcircuitry level of the system. We understand a neural system, but that is not enough. We have to understand how this behavior is emerging from the microcircuits, from the neurons and synapses, because ultimately we are going to configure those neurons and synapses and learn the weights for say. Unfortunately, when I started working on this field, I first studied computer vision, so I was very excited about computer vision. I studied visual neuroscience, but then I realized visual neuroscientists don't know much about the visual neuroscience system, the microcircuitry. As things is changing now, but that is because of lack of tools. It's not because they're incompetent, never a case. So I moved to a kind of system which people know a lot more. That is the olfaction, that is the sense of smell. And the goal is that after studying olfaction, I know there will be differences, but those ideas can be utilized for some other applications. So olfaction is a case study. Now I'm actually moving to tactile sensing. While olfaction, it has a unique long history of functional microcircuitry studies deliveries. We know the olfactory system at a very high level and also at the microcircuitry level. In visual system, we mostly know about it at the very high level, not much about the microcircuitry. And then this principle should be applicable for a wide range of applications. So olfaction. So what is this olfactory heart problem? What is this learning in the wild that I have been saying? Let's imagine a fox looking for prey. There'll be a strong target odor for his baby, or there'll be low background interference. This is an easy problem for the fox. Or there'll be weak target odor, and there'll be high background interference. This is a hard problem for the fox. There are so many odors. How is he going to recognize his odors of interest? Or he might have to learn something new. He might forget his previous learning if you think of ANN. This is the olfactory heart problem. This is what we call learning in the wild. Let's formalize this. This is very vague right now. We have to formalize this. So learning in the wild means, these are some of the characteristics. If you want to know more, look at my paper. Online lifelong learning without catastrophic forgetting. So in traditional ANN deep learning, what we have is we learn, say, two odors, apple and oranges. Later on, we are going to learn banana. We'll forget about apple and orange. That is catastrophic forgetting. But learning the wild doesn't allow that. You cannot forget previously learned things. And it happens in the brain. The brain doesn't forget previously learned things until it wants. Learning should be rapid, not like hundreds of epochs. And it should be from few examples. In addition to learning, there should be a classified confidence. You should be confident about the learning. That's also important when you have to know how to learn something new. One state, the order should be identifiable in highly occluded environments. There should be a technical from model scaling. I'll talk about that later. It's a bit technical thing. There should be a solution with sensitive. I'll cover that later. The network must be robust to wild polyvariant inputs. Again, wait, we'll come to that later. So these are the characteristics of learning the wild, and there are a few more. And we are trying to design an algorithm inspired from olfaction, which can learn in the wild. Now, don't get intimidated by this figure. This is the model of the olfactory bulb, rodent olfactory bulb. It's for the mice. So here we have the olfactory receptors. Odors are being received by the receptors, and then it is processed in the glomerular layer, where concentration tolerance and data regulation is performed. And then this information is passed to the subsequent layer of mitral cells and granule cells here, where the data is converted into a timing-based coding. Then these granule cells learn these odors. They act back on the mitral cells. The knowledge is filtered, and then this information is fed to higher brain regions like cortex. Cortex again talks to the olfactory bulb. But today I'm not going to talk about this entire architecture. I'm going to talk about only the olfactory bulb, few things to save time. So here's the figure of the neuron. How do you model this? So to model it, we started using the most simplest version of biologically plausible neuron. There are many fancy neurons now. It's just linear integrated phi neuron. So here you have an input. The neuron is receiving an input for a long time. Here the x-axis indicate time and y-axis indicate membrane potential evolution. So you could give the current to the neuron. The membrane potential is going to increase. At some point, the neuron is going to spike. It's going to reach a particular membrane potential value, and that membrane potential will be reset to 0. And then it's going to increase again. The neuron is going to spike again. Now, in this kind of spiking neural network, only the spike information is sent, nothing else. So use this alive neuron to model the mitral and granule cells. The parameters are different because they are neurons, but their properties are also different. One of them are interneurons, which we call it ghost neurons usually. Now, one of the other characteristics was gamma precedence coding. So you might have heard of all these alpha, beta oscillations, gamma oscillations in the brain, which you see when you put an E is a capital put this monk. So this is the same thing we are talking about. They have a very important role to play in computations. So we designed gamma precedence coding. This is a super simple thing. So you have sensor inputs 0.95, 0.4, 0.7, 0.2, and 0. As per this gamma precedence code, 0.95 will make the neuron spike first, followed by 0.7 and 0.4. Maybe 0.2 won't make the neuron spike at all. This spike timing based coding will be executed by the presynaptic neurons, which are the mitral cells here. And the postsynaptic neurons, the granule cells here, are going to learn those spike timing-based coding. There is a particular learning rule called STDP, which does that, but there can be other rules too. Let me skip that for now. These mitral cells you see here is an enlarged figure of the mitral cells. These mitral cells here, they excite the granule cells. Granule cells learn those order structures. If you're familiar with components, you can think that these granule cells are kind of learning edges and bars of images, like the first or second layer convolutional neural networks. And these granules again act on the mitral cells. Now, experimentally, it has been observed that granule cells act locally. They don't apply their inhibition, which is a particular property of neurons, on all the mitral cells. They act locally, and they actually purify the mitral cell input. They denoise it. I'll show you that later. Overall, this serves as a network called attractor. It's a physics-inspired concept, which I'll try to describe later. Okay, let's stop here, but we'll see. This dinner we discussed neuromorphic engineering, model computing, and olfaction. I showed you very briefly. I should describe you the olfactory bulb, which is comprised of the globular layer, and the external plexiform layer, which is comprised of mitral cells. These mitral cells excite granules, and granule cells locally inhibit the mitral cells. Now, let me talk a bit about some results. First, we designed something called EPLff, which is a feed-forward external plexiform layer. Then I'm going to talk about Sapinet, which is a much bigger network. We are now working on Sapinet V1. That should be out in like next few months. So you'll see me talking about that later. Okay, so these are embedded AI. So we have to select data sets which are compatible with embedded AI devices. So first we selected a very simple data set, which is called UCSD gas sensor drip data set. So UCSD is the university in California. They recorded this data set. So you have sensors, and there are 6 gases from which we record data: ammonia, acetaldehyde, acetone, ethylene, ethanol, and toluene. There are 13,000 samples. In embedded AI world, you don't get a lot of data. There's always a data scarcity. But the problem is this data is sensor-tricked. Some of this data are recorded in batch month 1. So there are few samples of 445 which are from month 1, but some of this data are recorded later after 3 years. That is batch 10. And they're separated in groups because they're sensitive, which means the sensor responses to the same gases are different when recorded at different time. Now we took this data and we first trained it on a multilayer perceptron, single deep neural network. You can go for advanced architectures too. We also did it on autoencoders. We first trained with ammonia and acetaldehyde. The performance was good, fine, we know that. Later on, we trained with acetone. The performance of the neural network dropped. Artificial neural network. Ethylene, ethanol, toluene, it dropped. Now this is a known thing. This is called catastrophic forgetting. This kind of neural network separate from catastrophic forgetting. Then we took EPLff, which is our olfaction-inspired network. We first trained with ammonia. The performance was high. Then acetaldehyde, acetone. The performance didn't drop significantly. So EPLff doesn't suffer from catastrophic forgetting. The learning rules are different. It is neuro-inspired. So it doesn't have the limitations of conventional computing architectures like neural networks. That is good. EPLff doesn't suffer from catastrophic forgetting. Next, I have been talking about sensor trait. So here, x-axis indicates 16 sensors, y-axis indicates sensor responses, the 6 gases. Colors indicate the gas types. If you look at the sensor responses in month 1, they're widely different from the sensor responses in batch 7, which is month 21. The sensor responses are different. They're sensor trait. And that's a problem because your learning becomes obsolete. The learning that if you train a network in month 1, but the same learning won't be applicable in month 31. You can model it, but when you're in the wild, that modeling doesn't work well. And it's very big problem because you design the sensors, but sensor vendors find it hard to sell it because of trip. You have to replace the sensors very often, and sometimes it is not easy. We observed that when you apply the data regulation methods from the olfactory bulb, you can recover well-behaved signals from event-degraded sensors. That removes hyperparameter tuning hurdle, so you don't have to tune the network. But you still need to retrain the network. So we observed the performance of EPLff, which was actually a simple network, on this drip dataset. Till that, the performance of this EPLff is better than any other published work. So we propose this rapid online learning as a solution for mitigating sensor drift, which I'll call very briefly here. So we train a network with this EPLff with these orders. Whenever there is a performance drop, it quickly learns. Learning here is rapid. And you know when to learn because you have a confidence here. And you don't have to know that, wait for the entire train set availability. You can learn with what is available. Maybe classes or samples. You can always update the model. That's the advantage. And then you don't have to care what hyperparameter you're tuning. That's one of the other advantages. And there are other few things too. So this is a very cool idea. And I wrote this paper in like 2009. I was very surprised that now there's a company in Germany who is actually thinking about implementing this there. So I didn't believe when I worked on this during my PhD, I was, okay, I wrote this paper. I was not very excited about this, but now I'm getting more excited when this company started pursuing this work. Okay, so we took this EPLff there, and we wanted to see, is this really restricted to olfaction? Answer is no. So we observed that this EPLff gave us high classification performance on satellite imaging data. So these are satellite data from hyperspectral imaging data. And if you look at the train set size while learning in the wild, it was only 7.6%. Usually in machine learning, we have 70 to 80% train set size. And then it also works on frog call classification data. So this is the data recorded in Amazon forest. And the pre-processing is done differently. And then we wanted to see if it works on EPLff. It gave us good classification performance. And the train set size was also small. So that's good. But again, EPLff, we know it was simple. It's an iterative procedure. We wanted to add more things to EPLff. So we designed Sapinet, which is a much bigger network. So I showed you this complicated architecture before. This is a much simpler diagram of olfactory bulb. If you're familiar with deep learning, it should be reasonably easy. There are a few things. You have the raw data, pre-processes, glomerular layers, and then it goes to the mitral cells. Mitrals accept granules. Granules from the mitral cells. There are tool connections, etc. inhibitory. There are some hardwired connections. There are some learned connections. And this information also goes to higher brain regions called cortex. Cortex also talks back. Let's ignore that part for now. Only talk about the bulb. This has 4 interesting characteristics. One of them is data regulation. Other is model scaling, classification, and denoising. And the metric we use is Jaccard. This is a metric learning. So we use Jaccard distance for classification here. Now, I'm going to talk about a few characteristics of Sapinet, not a lot. One of them is data regulation. Now, inputs in natural environments can be unpredictable. You don't know what is coming. And we are talking about spiky neural networks when it comes to in Loihi or other architectures. There, if there's no spike, there won't be any communication. So we need an assurance that neurons are going to spike. And that's a problem if neurons don't spike. The problem is that if it's an anomaly, it will never be detected. So here you see 3 wild order responses. So the x-axis here indicates 16 sensors, y-axis indicates sensor responses. These are 3 wild orders. Now if you look here, these are the 3 order indices here on the x-axis, and y-axis indicate the neuron spike count. So blue was fine here. Blue is giving some neuron spike count here, 0.5. Green is very low. But if you look at the red, no interneuron is spiking. So no neurons are spiking. Now this is a problem. You need to guarantee that neurons are going to spike. Because if red is an anomaly, we'll never be able to detect. So the solution is we apply signal conditioning so the network will just work on arbitrary data sets without hyperparameter tuning. This is again inspired from glomerular layer, olfaction. Let's understand this better. So here the x-axis indicate 100 sensors, mitral cells, and y-axis indicate sensor responses. If you look at the data, it is very, very wide. The same data, but sorted. If you look, they are drawn from different distributions. Now here the x-axis indicate 40 sensor orders here, and y-axis indicate the neuron spike counts. These are the mitral cell spike counts from this second layer, and the granular cell spike counts from the third layer. Now here in this data regulation, what we are seeking is our flat curves. You have these 40 samples, the spike counts for mitral and granular should be approximately similar, which means this curve will be flat, but we don't see that here. So we apply multiple steps. One of the significant steps is concentration normalized. We remove the concentration information that is inspired by biology. You see that the mitral cell spike counts are a bit flatter, but not much. And the data looks a bit more regularized. By regularization, I mean they follow a same like a distribution. We apply one more step that is inspired from biology. In biology, we don't have same parameters for the entire brain area. So there's heterogeneity. Now we wanted to understand whether heterogeneity is of any benefit. If there is benefit, why it is beneficial. So we introduce threshold heterogeneity, spiking threshold heterogeneity, and we observe that the curve, spike count curve lengths, they become much flatter. That was an interesting finding. Then we applied one more step, that is the final step, which is heterogeneous duplication. We observed that these ET cells here, they project randomly to something called mitral cells, which I describe later. ET are external tufted cells. If we make use of these sparse random projections from ET to MC, we observe that the data is regularized. They follow some curves, some distributions, except one, which is anomaly. That's an extreme case. And after that, we see that for all the 40 orders, 39 orders to be more precise, the spike count curves are flattened. And this is data regulation. This is what we are seeking. So multiple steps inspired from olfaction helped us receive data regularization. Now this is good. Okay. Now I talked about Sapinet. How is it working? We wanted to understand that. So here the x-axis indicate 16 sensors and y-axis indicate sensor responses. Red is the original data and blue is the corrupted data. Some noise is there, some noise. Now here the x-axis indicate mitral cell indices, here 100 mitral cells here, and y-axis indicate the mitral cell spike timings. Now if you look at the timings here, they are different for their real and the corrupted version. But Sapinet, when it is in action, after a few gamma cycles, the red and blue dots are going to overlap. So the noisy pattern is cleaned in successive gamma cycles. I give you a noisy order, the network is going to clean it. And when it happens, there is an overlap of blue and red dots. And this is how Sapinet works. It's a bit similar to autoencoder, but there are a few other properties they are like learning the while, which an autoencoder cannot do. And there is one more interesting thing called neurogenesis in Sapinet. So neurogenesis is a process by which new neurons are added in the brain. Now, there's no adult neurogenesis dogma for a long time. So Ramon y Cajal was a great Spanish neuroscientist. He was a Nobel laureate. He had an interest in the regeneration of the injured brain. If a brain is injured, can it be regenerated? He wanted to understand this. No AI, but it's more like a biology thing. To his disappointment, he could find no evidence of neural multiplication in adults. Until the 1990s, it was widely accepted that neurogenesis did not occur in the adult brain. So it's only like 33 years ago that neurogenesis came into existence. And rodent olfactory bulb has adult neurogenesis. That's one of the reasons I started studying olfaction. Olfactory bulb and hippocampus has neurogenesis. Not many brain lizards have that. We observed that if we have neurogenesis in the network, the classification performance is better than when we don't have neurogenesis. So neurogenesis improves classification performance. So why so? So what we observe here is that here x-axis are the granule cell thresholds and y-axis are the granule cell spike counts. We have 5 orders. They are sequentially presented to the network. Blue is the first one. When you don't have neurogenesis, the first one is going to be learned, but the subsequent orders, there won't be enough resources to be learned. But if you have neurogenesis, you have enough resources to learn all the orders. So the blue curve here overlaps with the red green curves. So the conclusion is neurogenesis restores the granule cell spike count, it's a particular neuron, and that improves the network performance. So neurogenesis is essential for olfaction-like data. It might not be very useful for vision. We can talk about that later. So till now, I talked about an olfaction-inspired neural network for learning in the wild. We observed that heterogeneity, which we know is present in biology everywhere. Biology, there is very little uniformity. It's important for network performance. Adult neurogenesis is essential for lifelong learning. Inhibitor drive on mitral cell but granule cell is columnar and is essential for data denoising. We talked about granules acting locally on mitral cells, and I showed you the Sapinet in action thing. Learning in the wild can mitigate sensor drift. We saw that. I didn't go into the detail today, but this network has features like spike timing-based coding, local accelerator, and inhibitor learning. And if you look at the desired features of something like Intel Loihi, these are the desired features. And in fact, we have a network. We have 2 networks implemented on Intel Loihi, 2 different versions. We'll have 1 more probably this year. And they make use of these features like spike timing-based coding, local learning rules, and recurrence. While it's a lot of recurrence, it's not only feed-forward. And recurrence, one active area of research is understanding how recurrent computation happens in the brain. Okay, now I'm going to talk about something else, which was the work I did in the Netherlands. We worked on radar inference systems, ultra-low power radar inference systems, using analog computing. As I said, analog computing, we do analog computing because it consumes significantly low power than digital systems. And the task was to design an ultra-low power radar target recognition system. Again, this is an industry, so we cannot go into the exact details because there are confidentialities involved. We can talk privately about these things later. So in this gesture recognition system, we have a radar, we make some gestures for performing some tasks, say to turn on a smartphone or turn on a TV and like changing channels kind of things. When it comes to designing these radar target recognition systems, only optimizing the network using some algorithm is not enough. We have to think from the sensors to the decoding part. So you have to optimize the signal processing, sensor data pre-processing. You have to optimize the detection, which is just that, encoding, and then you have to optimize the network, the training part, and then you also optimize the decoding. Only then you can claim that you have assumed ultra low power system. And I'd say you should also be very careful these days because I have been seeing a lot of papers these days in embedded AI. What people do is like, they write the paper, they only say our network performance is 60 milliwatt or 80 milliwatt, but then their entire system consumes 1 watt. That's not exactly ultra low power. You have to think about end-to-end optimization, end-to-end low power. It's kind of cheating. People do that. I have seen a lot of papers. And we designed the system, we observed that its entire power consumption was around 20 milliwatt if you take all the sensor to end-to-end power consumption. If you look at only the network power consumption, it is less than 1 milliwatt. It is super low. And the reason we were able to do it because it is analog computing. And the latency, the time to solution was less than a millisecond. Now, this beneficial, why do we care about low power? Not always. We care about low power when we have a coin cell battery and we want the battery to last longer. There we care about low power. Instead of 1 year, if you can make the battery run for 5 years, it's a huge benefit. So this is radar target recognition. Then we open something else called sequential neural machine. It's a generic concept. So we have a network in some embedded AI devices. You have a lot of sensor data coming in. It's always coming, but you cannot store all the sensor data. You don't have enough memory. If you have so much memory, you need a lot of space, you need a lot of power. You cannot sell this system cheaply. And sometimes there is an area constraint in embedded AI systems. You want to fit it very near the sensor, but if you have so much memory requirement, you cannot fix it. What do you do? So we have a network. What we design is a sequential neural machine. We have a network. We'll take some outputs from the network while it is being trained, and then we'll store it for some time and feed it later by some connections. And how we feed it, we'll learn by backprop. So in addition to training the network, we'll also use this backprop to learn how to use the previously old information. And in this way, it's kind of similar to LSTM, the few things that they're getting, but those will be hardware information. You can call it hardware LST gates here. So these memories and all these delays, this hardware information will impose hardware constraints here. And those information will be there. And the entire hardware will be optimized along in that way. Solution which we kind of very simply says, allow the network to forget. You don't have to store all the sensor data, but you remind it later that you have also this information from previous. In this way, you don't have to store all the sensor data. Store what is for some, you like break down the data, store it in chunks. And we observe that even if you do this, the classification performance is similar compared to when you fit the entire sensor data, like for like 100 millisecond or 100 hours of data. If you fit the entire data, that is the performance is similar. So that is great. This reduces the memory consumption a lot. This is sequential neural machine, and we tested it on audio keyword spotting task. It should be generic. We haven't tested it yet. We haven't got the time. It's another research area we have to do. It should be generic concept. Okay, so I'd like to thank my advisor, Tom Tellen, my committee members at Cornell, Al Moller, David Phil, David Smith, and Thorsten, my lab members, especially Matt Ayon, Jesse, Michael. Christian was a collaborator. And then I'd like to thank my Amir and Vasily from the INATRA team in Netherlands. And the funding analysis, Intel, Cornell, and NIH and Cornell SACE fellowships. We are almost at time. Okay, there is one more thing. I am hiring. So I'm hiring PhD students in the AI department. The applications are going to open on 5th of March. Details will be available then. If you're interested in working on embedded AI systems, deep learning, neurofit computing, or computation neuroscience, send me an email, then we can figure it out a particular project. Okay, that's it. I'll stop here. We're on time, right? Okay, thanks. Questions?
Thank you so much, sir. Yes, we have questions in YouTube and I think in the Google form as well. So first, I think I'll ask a few questions from YouTube. So this sir is asking, could you please highlight on the ethical considerations before conducting neuroscience research? Are these datasets made available to the public?
Oh, that's a good question. Right now, so I personally don't do wet lab experiment. So I don't go and kill an animal and do record data from them. So I'm on this in the safe zone in that way. I collaborate with neuroscientists, and the data is publicly available in US, especially if NIH is funding, that is mostly the case for neuroscience experiments. They are bound to make the data public. They're bound to make those research findings, and there's no other data concerns here. There's ethical concerns when it comes to embedded AI designs because people care about privacy. Think about it. So if you have a headphone is always on, it'll be a problem sometimes because it might spy on you. The data will, so those things that when it comes to designing embedded AI, we have to take those things into account. That is the ethical concern always there. But that people talk about that even in general AI. In neuroscience, I don't see ethical concern for me because I don't do experiments. But yeah, for neuroscience, people who are doing neuroscience, like they are not concerned about AI. They are doing neuroscience by understanding the brain. They do have a lot of ethical concerns, I know. Like if you're studying monkeys, you can get only 2 monkeys. If one of them dies, then it becomes a problem for PhD students to graduate. It takes a significant amount of time to graduate. In neuroscience, it's a problem. So people are moving away from monkey experiments these days, and they're moving to smaller animals. Now, there's one more thing there, which people are working on. It's not convincing yet, something called organoids. So there, people are trying to design artificial brains, but not like animal. They are taking inspiration from the animals, but they're doing it in artificial. That avoids killing animals. It's not very convincing yet. You do see these oscillations here, but like I think a lot of research need to be done there to actually take inspiration. Anything else?
Yes, sir. Thank you. So Shishi sir is asking, during training, what kind of objective function does SSM solve?
So it is SNN.
SNN.
That's a interesting thing here. So we are talking about learning in the wild, right? So right now is an open question. What kind of objective functions you'll have? We actually don't. These are attractors. So we give you a noisy voice, it's going to clean it. So there we don't actually create a loss function in a conventional way, where we have labels and we have some data and we are just trying to optimize. We don't have that because we don't know what are the labels. You'll have some information, but not all. So in learning the wild, we don't have that. So the training rule is different. If you're talking about this bio-inspired network, the thing that we use called attractors. And that's where the novelty is. And that's where we actually disaggregated it. Because it's different. Now, there's one more thing which I talked later on, which was the sequential neural machine and the radar. That was actually deep learning. So our loss functions are SNNs, spike counts, and we use something called surrogate spike gradients. So idea is that in the forward pass, we assume that these are deep neural networks. We'll have some, and when you're doing backward pass, we assume that it is a smooth function, but not a spike. It's an approximation algorithm. If you're familiar with algorithmic approximations, it comes under that domain. There is a bias there, a bit of bias, but not more. People are not a lot, and when it comes to embedded AI, that bias is fine. So there your objective functions are conventional deep learning objective functions, and that is meant for that. So we don't do learning the while, we're only doing inference, and you train with conventional deep learning tools. You just change few things, like you change the activation function, you change your loss function, the way you use the same loss functions like at optimization, but use the same optimizer like Adam, but your loss functions is a bit different. We use time to first coding sometimes. Which neuron spike first in the output layer? That's one thing we do. There's actually another active research area. We are continuing using optimizations like Adam, SCDT, but it's not very convincing that they are the way to go. So people are trying to optimize that and try to see if something better can be done. And some cool things are going on there. So one of the things people are saying that we probably are fine with something like synchronicity. We don't need Adam here when it comes to spiking neural networks.
Thank you, sir. We have a question by Bharti Mishra, and she's asking how to solve von Neumann architecture problem in different algorithms. It's a direct question.
Von Neumann architectures in different algorithms. I didn't understand the questions. Can you please repeat?
So yeah, she's saying how to solve von Neumann architecture problem in different algorithms.
Okay, so let me be more clear. So we have these von Neumann computing architectures, which we have it everywhere, right? We have in our computer everywhere. That is all von Neumann computing architectures. We have a memory of a computing unit separated by bus. That's existing everywhere. The algorithms are already present there. Neuromorphic and algorithms are non-von Neumann. You have a memory and computing, they are co-localized. Because they are co-localized, there's a lack of algorithms. How do you actually design these massively parallel algorithms? So a thing that probably you should think is Amdahl's law. If you want to parallelize a system, like you want to reduce the number of sequential components. And when it comes to this non-von Neumann computing architectures, we have to think about that, like how to reduce the sequential components. Von Neumann algorithms, there's a lack right now. Brain does in a non-von Neumann way, and that's why we're taking inspiration from the brain. Few things, there are very high-level things. It's 1 hour is not enough to talk about these things. So here, your learning ideally has to be local. You don't actually use like a backprop lab algorithm. Ideally, the brain doesn't. So in the brain, communication happens locally, and that's also power efficient because there are so many wires there in backprop and UTLs and a backprop network that itself takes a lot of resources. So in the brain, that doesn't happen. There's a local connection there, and there's some few complicated connections. There's sequence there. There's local learning, as I said, inhibitor and excited learning. All of them allow the brain to do non-von Neumann computing. Approximation is surrogate gate addition, which people use these days. That's also kind of non-von Neumann computing. We have one way of designing non-von Neumann computing algorithms. Again, active variations, but there's some message with the brain. You cannot say that the brain is doing it in this way. There is one more thing which people are working on there, which might sound interesting. So we have this von Neumann computing architecture. So the von Neumann algorithms there, which are used everywhere. Can we use it in neuromorphic chips? You don't have max there, or you don't have all. So there is a work going on there. What people are trying to do is like using timing as a pseudo for doing multiplication there. It's like 1 or 2 papers. It's not very convincing yet. So that's why I'm not very inclined to us talking about that. But people are working on this. So if you want, you can look at this work from, I think it's a work from Berkeley, Redwood Center for Theoretical Neuroscience. You should look at that work. There's one more probably work from, there's one more work from Heidelberg, Human Brain Project. If you look at their work, so they also did something there, how to use the von Neumann algorithms in non-von Neumann computing architectures. These are very recent work. So these are not exactly used in industry. These are mostly academic work. Okay. Any more questions?
Thank you, sir. Yes, we have just 2 more questions, which are little general questions. So I'll ask them quickly. First is from Dr. Shakuntala Chaudhary. She mentions healthcare is at an inflection point. Through a combination of technology and expertise, we are helping organizations build a more resilient future. Please comment on the pros and cons of AI ML in healthcare. Pros and cons of AI in healthcare.
Well, pros and cons of AI, well, it's a very controversial topic. It also depends upon which place you are in. My views will mostly be from abroad because I stayed outside India for a long time. I'm still very new in India here. I'd say one of the reasons things I always say is privacy. We're talking about embedded AI, and right now we have to be very careful about where to put this embedded AI systems. So in the embedded AI systems that we are talking about today is always on systems. So these are machines which will never be turned off. There's a huge possibility of this system spying on you. So there's an ethical concern there, as I see it. They can steal your data, and if this from China, you don't know what's going to happen. They're going to just make use of this data and spy on all your lives. So something has to be done there. We have to be very careful about the part. Again, of course, the data. We need to be very careful about the data. We Indians don't care a lot about sharing our data. But in abroad, people are very careful about sharing the data. They don't like sharing their email IDs, and I believe that's very important. So that's another thing we should be careful. In embedded AI, we are not very concerned about data because we don't have immense like data anyway these days. So in embedded AI, companies collect few thousands of data and they don't make it public. And there's one advantage here when it comes to this model computing kind of things. You'll be training very few about when you have to put a network. Everything else is going to happen inside the system, and the hardware is going to die after you're going to use it. There's both pros and cons here. Just like think about it as humans. We are in AI. If you are in AI system, you're in AI systems. We sometimes behave weirdly. The systems might behave weirdly. Can we do something to get rid of that? That's a concern we have to address at some point. Nothing else. No.
Okay, thank you, sir. Finally, we have one more question from Shishir, sir. He's asking, what will be your suggestion to EC or CSE grads who want to pursue research on neuromorphic computing? So how should college students basically start if they want to pursue neuromorphic computing?
Okay, so neuromorphic, like many people tell, I'm also going to say the same thing. It's an umbrella term. A lot of these things fall under this. If you're an ECA guy, I would say you should definitely learn a bit about computer architectures. Signal processing is very important. Of course, traditional machine learning. These are very important courses. Then the other part you need to learn is you need to take a neuromorphic course. Or maybe a computational neuroscience course. Even that is not enough sometimes. There's a big difference between computational and neuromorphic course. Right now, there is a lack of neuromorphic course. We have that in IIT Hyderabad right now. IIT Bombay has one neuromorphic course. They are mostly focused on hardware. IIT Delhi should have one too. IIC should have one too. I'm not familiar with any other places, honestly, in India. It's maybe because I'm very new here. So to know the neuromorphic part, you can probably read some books. So you can read some computational neuroscience book. You can read a book called from Carver-Mate, who was a pioneer on neuromorphic media. He wrote a book on LFVLSI in 1989. I also read that book. It's an old book, but he will give you some motivation. For CSA guys, I would say learn a bit about statistics. Usually what happens, I've observed that CSA guys are not very good at statistics. It's a general observation across the world. Learn a bit about statistics. It's very important. And also computer architectures, and also again signal processing. That is something CSA guys don't only spend a lot of time. Computational neuroscience you should take, and also neuromorphic computing, as I say. Again, neuromorphic computing right now, especially the AI part, like what is SNN? I talked very briefly today, and there's connections. There are not many courses right now. IIT Delhi, Hyderabad should have. IIT Hyderabad, I'm teaching it. IIT Delhi should have one. As Bombay definitely has one. Hardware. IIT should have something similar. I don't know what is there in IIT Guwahati, to be honest, in neuromorphic. And there may be some other online resources. So I have seen some good, nice GitHub people creating some GitHub repos. You might want to read them. It's a little more like a bird's eye overview kind of thing. You won't get an in-depth knowledge. So it's only for your general knowledge. Don't expect that this will give you an in-depth knowledge. And if you want to know more, just send me an email. I might be able to send you some book links. Okay, this might be things that might help you based upon your background. Anything else?
Just on that, sir, for some clarification, are these courses that you mentioned for undergraduate students or like those who are going to take masters and tech?
So let me tell about my course here. So they are PhD students, they're master students, and they're final year undergrads who are taking it. So usually we expect them to know a bit about computer architecture, signal processing, a bit of machine learning, deep learning. And then you are the stage to take something like neuromorphic AI. That happens usually, but even in the AI department, that happens after your third year, in your fourth year. So undergrad 4 years, MTechs and PhD students, first, second years is also third year. There is a kind of students that should take it. But there's one more thing here. So ETH Zurich, Institute of Neuromorphics, they actually have a dedicated neuromorphic engineering course. There you'll start learning about neuromorphic right from the first year. So you might want to look there. And probably Germany should also have, and probably TU Munich or somewhere, they have a neuromorphic master's course these days. And ETH Zurich definitely has a PhD in neuromorphic computing. Anything else?
Thank you so much. So I think that wraps up all the questions, and we are also at time. So thank you so much, Dr. and Borthakur sir, for this amazing session. And I think you definitely, everyone was very sort of, I think, engrossed in the entire session. And yeah, I think with that we can end today's session. Shivu sir?
Yeah, we can. Thanks for your very informative and excellent session, Ayon. And you did very excellent work, and I think people already motivated on your session. And another thing is that I want to ask is that in the beginning of your talk, you mentioned about forward algorithm that Intel proposed. So is there any relation with neuromorphic AI? And second thing is that is it faster to train compared to backpropagation?
Yeah, so forward algorithm, so it actually is neuromorphic oriented. That's the way I'd say. I'll tell you one reason, very obvious reason. When you're doing backprop, we are doing forward pass, like in a backprop 10, we are doing a backward pass. Here, when you're doing backprop, in neuromorphic chips, you will have dedicated wires that you can get rid of in forward algorithm. And making this neuron complicated is not a very hard thing. Neurons in a brain are anyway very complicated. So forward algorithm is definitely going to optimize power. In fact, I actually have a student working on this year. So there's one more work from Harvard, similar direction, where they are trying to do 2 forward passes, and they're trying to optimize the training. So this is a very active area of research in neuromorphic computing. I didn't say computing, I said neuromorphic AI, algorithm design.
Okay, thank you. And Sakuntala ma'am asked you one question that regarding health-related thing. We can ask you. So she told actually great work, and I'm just reading her post from YouTube chat. So great work. I heard about Ayon from my brother Deep Medi of National Science Foundation. So Sakuntala ma'am is the elder sister of Deep Medi. I think you know him. So, and she is asking, like, are you visiting USA again as visiting professor? So,
Well, I don't know. Maybe, maybe later this year. I'm not sure yet.
okay, thank you. Abhigyan, I think we can wrap up. So,
Okay,
Yeah,
I'll leave that. It's already 8. Okay, I'll leave. Bye.
so